Now let's take this question. Here we have to apply Green's theorem in evaluating this line integral. Line integral is y minus sin x dx plus cos y dy, where it has to be evaluated on the curve where C is the triangle enclosed by the lines y equal to 0, x equals to pi, and pi y equals to 2x. So let me first draw these lines and get an idea about the curve along which we have to evaluate this line integral. The curve is triangle. So let me draw this. So let me draw all these lines and get the triangle. So this is the curve we are looking for. These are the lines. This is x equals to pi, this is y equal to 0, and this is pi y equal to 2x. So we have to evaluate it. We have to evaluate it on this curve. So we have to use Green's theorem. We will use Green's theorem. So from the Green's theorem, we know that m dx plus n dy equals to dn by dx minus dm by dy into dx dy. So here I'll make one point very clear. See, I have oriented this curve in this direction, but this line integral, when the curve is oriented in this direction, is not equal to this double integral. In Green's theorem, it has been clearly written, if you carefully see, it has been clearly written that the curve has to be oriented. This is double integral. This double integral is same regardless of the orientation of the curve. Regardless of the orientation, double integral remains same, because double integral does not depend on orientation. Double integral just depend on the region of integration, which is the area enclosed by this curve. This depends on R. Your R is going to be this. This is your R. But this double integral, which is same regardless of the orientation, this double integral cannot be equal to the line integral along this orientation, and it cannot be equal to line integral along this orientation. It can be equal only to the line integral in one of the orientation, because the line integral, if carried out in the two orientation, differ by minus sign. So your line integral cannot be equal to say plus 10 and minus 10 at the same time. So this line integral is equal to the integral which is evaluated along the orientation, such that if you move along this orientation, this region R should lie on the left. But the orientation which I have drawn, which I have deliberately drawn just to make this point very clear, if I evaluate the line, if I evaluate this double integral won't be equal to the line integral which is carried out in this orientation. Why? Because if say I move along this orientation, then this region R lie on the right. So this double integration will be equal to the line integral which is carried along this orientation, that is an anti-clockwise direction. So if, though in the question it has not been given that nothing has been told about the orientation, but if sometime they ask you evaluate line integral along this orientation, we can still use Green's theorem. Green's theorem, this double integral will be equal to the line integral along this anti-clockwise orientation. Whatever answer you get, you put minus sign, you get the line integral along this orientation. So what I am right now, what I am doing is I am calculating the line integral using Green's theorem. I will calculate first the line integral along this orientation. I will calculate double integral, which will give me the line integral along this orientation. Because if I move along this direction, the whole region of integration R lie on the left. I'll repeat it once again. See, this is a double integral. This double integral does not depend on the orientation of the curve, whereas line integral does depend on the orientation. If I calculate a line integral along this clockwise orientation, and again I calculate line integral along anti-clockwise orientation, their magnitude will be same, but the sign will be opposite. If line integral along this clockwise orientation is plus 10, the line integral along anti-clockwise orientation is minus 10. So this double integral being a unique number will be equal to line integral along one of the orientation. It cannot be simultaneously equal to line integral along clockwise and line integral along anti-clockwise. So Green's theorem makes it very clear that the double integration is equal to the line integral which is evaluated along the curve, which is evaluated in the orientation, such that if I walk around along this orientation, the curve should be lying on the left. The curve should lie on the left. So let me evaluate this line, this double integration, which will give me the line along this orientation. And if I am asked to find line along the clockwise orientation, it will be minus sign, right? So I'll evaluate the double integration, this double integration over this region R. So what is M and N? This is your M and this is your N. So your M is y minus sin x, whereas your N is cos y. So from here dm by dy is 1 and dn by dx is 0. So your dn by dx minus dm by dy will be minus dm by dy. This is going to be minus 1. So your RHS, this RHS will be equal to minus of dx dy, which is nothing but area of the triangle. Nothing but area of the triangle. So this will be equal to what? This will be equal to, this is the base is pi, and I have to evaluate what is this point. This point will be, this will be pi 2. So the height is 2. So 1 by 2 base into height comes out to be, pi is the base and 2 is the height. So this comes to be minus pi. So this is RHS. This is RHS, and this will be equal to the line integral which is evaluated along this orientation as per the Green's theorem. So if I want to find out line integral around this orientation, it will be minus of this. So your required f dot dr is going to be plus pi. Alright, now I'll come to the next question. The question reads, apply Green's theorem in plane to evaluate 2x square minus y square dx plus x square minus y square dy, where C is the boundary of the surface enclosed by the x-axis and the semicircle. Now here also let me draw this curve so that I can get an idea about the region of integration of the double integral, which I'll convert this line integral into. So I'll have to use Green's theorem. First let me plot the curve C, which is the boundary of the surface enclosed by x-axis and semicircle. So I have to plot x-axis and semicircle. Let me first draw these curves and get the idea of the surface. So this is the semicircle and the curve is, so this is the semicircle, this is the x-axis, this is the curve. This is the curve we are talking of. So we have to use Green's theorem in evaluating the line integrals. So let me orient the curve in this direction. Nothing has been told about orientation, so I'll take anti-clockwise orientation by default. So from the Green's theorem, mdx plus ndy is equal to, it is equal to dn by dx minus dn by dy dx dy, where this line integral has to be evaluated along the orientation such that this region R should lie on the left if I walk along this orientation. So it is lying on the left. So this double integral will be equal to the line integral evaluated along this orientation. If ever you are asked to calculate the line integral along the opposite orientation, you just take negative sign of this double integral. So I have to evaluate this double integral. So this is your M and this is your N. So your dn by dx is 2x and dm by dy is this will be equal to minus 2y. So this double integral becomes equal to 2x, this is plus y dx dy, or this comes out to be, this is x dx dy, and this is 2y dx dy. Now I just see this double integral. If I evaluate it over with respect to x first, what will be the limit? The limit will be from minus a square minus y square to plus a square minus y square. See, this arrow intersect this curve. If I draw an arrow parallel to x-axis, this is where the arrow intersect, and this is x equals to minus a square minus y square. X will vary from this, from minus a square minus y square to plus a square minus y square. So you can see the limit is of the form minus to plus a, and you have an identity in definite integral which says that fx dx from minus a to a is equals to twice of 0 to a fx dx if f minus x is fx and f it is 0, and this is equal to 0 if f minus x equals to minus of fx. Means if this fx is even, this will be twice of 0 to a, and if this is odd, it will be, this integral is going to be 0. The same is the case over here. See, I'll advise you, remember this identity. This is very, very important. So this identity of the definite integral will make this equal to 0. And over here, if you see over here, what is the limit of y? If I draw an arrow in y direction, it will be y is varying from 0 to a square minus x square, and y is varying. I'll take the limits. So see, I'll take the limit first with respect to y over here, and then with respect to x over here. Or it's better if I convert it to polar coordinate. Converting it to polar coordinate will be very easy. So I won't take these limits. I'll convert simply into the polar coordinates. See, whenever you are given circle, it's always better if you convert it to polar coordinate. So this is equal to twice of y dx dy. So I have to evaluate this double integral over this region of integration. So converting it to polar coordinate, I'll get r sine theta, r dr d theta. R is varying from 0 to a, and theta is varying from 0 to pi. So this will come as r square dr. R square dr, where integrated, will become r cube by 3, and if I put this limit 0 to a, this will become a cube by 3. So this is 2a cube by 3, and sine theta d theta integrated from 0 to pi. So this will give me 2a cube by 3, and the integral will be minus cos theta from 0 to pi. If I put these limits, this will be equal to 2. So this is 4a cube by 3. Hence this double integral comes to be 4a cube by 3, and this will be equal to mx plus n dy, mdx plus n dy. So this line integral using Green's theorem